So today we are going to, as I said, to continue with the compensation through the phase lead. Okay. Remember, we said in phase lead compensator, we will be adding phase to the system, but at the same time, once we add a phase, we are going to add a corresponding gain also as well in this area. Okay, so let me repeat the design procedure for phase lead design. First of all, we evaluate the uncompensated system phase margin when the error constant are satisfied. That basically, the first thing we will do, as a matter of fact, we try to correct for any steady state error. And then once we do the correction, we will plot the body plot of the system with corrected steady state error. And from that system, okay, we read the phase margin. Okay, so suppose I have the phase margin of the system is giving me, let's say, phase margin from the system equal 20, and I need phase margin of, let's say, 50, then what the compensator should give me, how much the compensator will give me. شباب
انقطع الصوت يا دكتور.
غريبة، يعني أنا بالمكتب غريب. الحين واضح؟
ايه رجع
الحين واضح دكتور.
I don't know what happened. غريبة هذه. We should sue الجامعة. أنا بالمكتب بالجامعة مش مو ببيتي حتى just to avoid مشكلة الإنترنت. So all of a sudden I discovered that I'm talking to myself. Okay, so let me repeat the procedure. First of all, if we have a system, we evaluate the steady state error. If we need to satisfy certain steady state error, so we will evaluate the steady state error, and then we make the body plot of the system after the correction of the error. Okay, so suppose with that, I have, I will find the phase margin, and suppose the phase margin, let's say 20. And I need phase margin of 50. So how much the compensator should give me?
$30.
Okay, so the phase margin, okay, from the compensator will give me 30. Let's say this is 30. But look, if you add the 30, so okay, so once we have this one, okay, so once I have the phase which I want, I can find alpha. Remember, in the design, I have to find alpha, tau, and k. So now I can evaluate alpha from the how much compensation I am going to give, how much phase I am going to add to the system. So already I have, alpha is done. Now I need tau. How do I find tau? Tau will be depend on where do I position my compensator. Usually we said, remember, we need 30, so I must position it in the same place as the phase margin, because I'm adding the phase margin of the original system and then the 30 plus. plus the 30. But by adding the 30, look how much I'm going to add in here, how much magnitude I'm going to add.
20 log A.
Extra gain. What is this? The gain. What is this gain?
This 20
Remember,
log
we
A.
said this is it happened at this point, which is basically halfway. So this is the 10 log alpha. 10 log alpha. So what I will do in order for me to find this position, when I add this, okay. So how do I, where do I find which frequency will give me this? I will go to the body plot of the uncompensated system. Okay. I'll go to the body plot of the uncompensated system and I will look for minus this quantity in the uncompensated system. Okay. So basically, if I add this amount, add the point in here with where I read the minus, what will be the net effect of those two? I'm going to the, the body plot of the original system and look into the minus 10 log alpha. I know what is the exact quantity because I already determined alpha.
It will be 0 dB.
So it will be 0 dB. This 0 dB is my new crossover frequency. Okay, this is my new crossover frequency. And once I have this one, okay, then I can determine, because tau is related to the maximum frequency from this formula. So if I determine omega, then I can determine tau. Once I determine tau, then I will determine the zero and the pole of the system. The last thing I will do, I will set k equal to alpha in order to make the steady state error, there is no effect of the compensator on the system steady state error. That I will force GC of 0 equal to 1 by selecting in here, by selecting k equal to alpha. So this is basically the procedure. Let's take an example to see how does this work.
هذا دكتور
تفضل.
الجراف الموجود هنا هذا المفترض يكون 30 degree phase ولا مش هو؟
يس هذا اللي المفروض يعطيني 30 degree phase اللي انا احتاجه.
المفترض بس احنا نبغى 30 degree phase على يكون في الكروس اوفر فريكونسي صح؟
الكروس اوفر فريكونسي الجديد. يعني basically look انت what you are going to do, okay, look maybe in the example let me clarify it in the example if you don't mind.
ان شاء الله تمام ان شاء الله.
Okay, let's take an example. Suppose I have this example. In here, given a unit feedback system with the following open loop system. K in here in this particular case is not given. This is, adjustable. Design a phase lead element to satisfy the following requirement. So I need steady state error, okay, KV equal to 20, and phase margin of 50. Okay. Now, what is KV in terms of the system in here? So what's KV equal to in terms of the system? I would like to determine first of all K, which will give me this steady state error constant. So KV equal to what?
Limit as S goes to 0 of SG of S.
Okay. So this is equal to limit as goes to 0 S K 4K, sorry, over S plus 2 okay, which is equal to the S will go with this S will go with this S, and I will have what? 4K over 1. This must be equal to,
4K over 2 دكتور.
okay, sorry, over 2. S0, okay? So basically K equal to what? K equal to 10. And that will do the job for me. Is this clear? This is, we satisfy the steady state error. The first condition
Yes,
we
doctor.
do before we add the compensator. Okay, now I want to make the body plot of G of S with the new gain. So G of S equal to 40 over S plus 2. But let me put it in the standard format. J omega. What do I do in here? This should be J omega,
over 2 plus 1.
which means that I have to put 2 in here, isn't it?
Yes.
I'm taking the 2 out. So G of J omega equal to 20 over J omega over 2 plus 1. And this is what I want to sketch. And this is what I will do. This is the graph. Okay, this is the graph of the modified system to satisfy the steady state error. Look, this is 1, so it means that I'm taking 20 log of the 20, which is going to be about 26 or something. Any question here?
Clear دكتور.
Clear?
Yes.
Okay, now I need to satisfy the other condition. The phase margin, sorry, I needed 50. So the first thing I will do, let me find the phase margin from here of the system. What is the phase margin of the system itself?
We go to the 0 dB and find
Okay.
the frequency.
You go to the 0 dB and go down.
It's
Yes.
about 20 degrees.
What?
20 degrees, doctor.
If?
It's about 20 degrees.
What do you mean 20 degrees? Oh,
Phase margin.
the phase, okay, the phase, yes. So basically, this is the 0 dB, and that will give me about, to be exact, from using MATLAB, it will happen at frequency of 6.17, and the phase will be 17. So I will be using this 17, and I add to it the difference. What is the difference? How much I should add?
33.
33. Okay. Usually, the design look, it's trial and error, and it is how much you are comfortable with things. Usually, you put what we call safety factor between 5 to 10. It is not necessarily. It depends on the designer. Suppose I add 5, so I need to add 38 degree of phase margin in here, in this area, around this area.
دكتور,
Yes.
does this vary like with how big the phase margin is? يعني لو كان الفيز مارجن مثلا كبير 100 دقري كم حناخذ الاكسترا؟ لسه 5 او رقم اكبر؟
It depends. Usually, as I said, usually between 5 and 10. It's totally up to you. يعني ما في rule, ما في use this one. It is,
يعني قصدي السكيل.
maybe what you will do, okay, you try one, and if you don't like it, repeat it. Just, reiterate.
قصدي دكتور يعني
Or
السكيل ما
zero.
يفرق
You
إذا
don't have to put.
بس قصدي دكتور السكيل ما يفرق إذا كان الفيز مارجن كبير أو صغير.
الا يفرق اكيد، بس انه زي ما قلت لك يعني هو الديزاين بس بعض الاحيان لوك ريمبر يعني انت up to certain phase margin you can add in from your compensator. You cannot go beyond 60 to 70. So the system, I mean, there is limitation. The maximum phase margin in here you can add about 60 degrees. So if this become, يعني, let's say it is required from you to be 60, you cannot add the 10 point, because yes, there will be certain limitation. The maximum the compensator will give you 60 degrees, 60, 65, within that range, not more. So if you need more, then you have to have another stage of leading compensator. Okay, so look, if we add the phase in here, remember, what do we add also with it? If I add, okay, first of all, okay, with this one, can I determine alpha? Remember alpha?
Yes, alpha is 1 plus sine phase M or 1 minus sine phase M.
So this is alpha. I will determine alpha. Okay. Now, as I said, if you go back to the compensator, the shape of the compensator, okay, I'm adding the phase of 38, let's say. There is corresponding, gain I'm adding to the system. Remember, I'm adding this one at the phase margin, but when you add in here this positive quantity, okay, first of all, how do I determine this? Where do I find this quantity which I'm adding? Okay, I'll try to go to the uncompensated system, okay, and read minus, let's say, I look into this quantity in the negative from the uncompensated system. That's basically in here. Look, the uncompensated system is the blue one, and I'm adding the green is my compensator. So this point, basically the 6.2 dB, okay, I'm adding it to the system. So I will read what is this frequency in here. I will read, okay, first of all, I will go and find what is minus 6. Okay, from the original system, I will read at minus 10 log alpha, which is, let's say, 6.2. So I will read from here. Then if I add this to this one, what will happen to the overall system? What will happen? What is dB of the overall system? In this place, I'm adding 6.2. What I'm saying, I read it, where do I position? I position at place where it's minus 6.2 in the uncompensated system. So I put them together in that frequency. What will be the overall gain in there?
0.
0. And this is my new, okay, this is my new, okay, crossover frequency. This is omega m, which is, if you remember, if you look at it, you compare it to the original crossover frequency, phase crossover, gain crossover frequency, there is slightly shifted. And there, remember, it was 6. By the addition of the compensator, we are moving it little bit to the right. Okay, once I have this frequency, I can determine tau, and then remember the 0 is 1 over alpha tau, and the pole is equal to 1 over tau. So I will be done. So omega 1, okay, which is the 0, is 4.4, and the pole at 18.4 radian. Then my system, this is what I'm going to have. What I want to do next is, okay, I have to eliminate. Is there any error in here now? What will be the error? There will be an error because remember we need GC of 0 equal to 1. That will not create, that will not change the error which I already adjusted in the system. Okay, so in order for me to make this condition, I have to take K to be 1 over this quantity. Or my design is going to be, this is basically what I need. This is my design. This is the compensator, which will give me the complete design. Any question now? Any question? Shabab, do I lose you?
No, it's not okay, Doctor.
Okay. So this is basically what we want to do in the, phase lead design. There is another example because of due to the time, we are not going to go through that one, but you can read it. So the limitation which we have said in the design in here is that, if you need more than, let's say, 60 degree in phase margin, you cannot have it from the phase lead compensator. Either you use another stage, or you can go to what we call the lag compensator. Okay, let me go to the, if there's no question, I will go to the lag compensator. Okay, now, as I said, we would like to go to the phase lag compensator. In the phase lag compensator, okay, hopefully we will, by the way, we try to also, I hope we can do it, we try to do the compensation using the root locus. I hope by Thursday we'll do it. Okay. So the lag compensator, it has similar structure to the phase compensator. However, now we will have the pole is smaller and it's near the j omega axis. Okay. So in phase lag, okay, the angle which we are going to add is going to be negative or positive. Phase lag, what does phase lag mean?
The current lag, the voltage.
or in this case, basically it is, the angle of the denominator is greater than the angle of the numerator, which means I have, the overall angle is going to be negative. Now, if I want to do the body plot for this one, how does the body plot of this compensator will look like? First of all, I will have this constant. So I will start by constant. Until where? Now okay, which one will happen first? The pole or the zero now?
The pole.
Okay, which means that I'm going to have minus 20 dB per decade. And then, okay, it will level because of the zero. So basically, this is what we have. This is what we will have. Okay, the difference between the pole and zero is going to be 20 log alpha as well. And the phase, look at the phase. The phase now is negative. Okay. So it, as I said, it's very similar to the lead compensator. However, the position of the poles and zero are reversing. Okay. The lead compensator, in the lead compensator, we increase the stability and tune the steady state error by increasing the phase at the crossover frequency. We are adding phase at the phase crossover frequency. In the lag compensator, we should have similar impact. However, the approach is different. Okay. By decreasing the gain crossover frequency comes down to a frequency at which the corresponding phase is higher. I will come and explain this one graphically in a moment. The objective of the phase lag compensator is to move the gain crossover to a lower frequency while where the desired phase margin is realized, while keeping the phase curve of the body plot relatively unchanged. Okay. The drawback from the phase margin, from the phase lag compensator is that you will decrease the bandwidth, which means that your system becomes sluggish. It's going to be slower. Any question here? Roughly speaking, let me try to explain in here. How does it work? And next time we will take definitely an example, or maybe we'll start again. Okay. So suppose I have, this is, the black one is the uncompensated system. Okay. And suppose you are already satisfying the steady state error. So now look, what is the phase margin? The phase margin is 20. Okay. Well, if I want to go to, let's say, phase margin of 50, I have to add how much? How much phase margin I have to add? If my desired, okay. Shabab, what's wrong today? The class is, what? Are you busy with the quiz or what?
يا دكتور يعني سامعين وكذا بس
بالضبط.
we don't have the power to respond.
Exactly. It will be difficult. So what do you want to do? So in this case, okay, we will leave this point. What we try to do, we take the phase margin from here. Let's say I need 50 okay, or 45. So I will take the 45 plus the 5, which is, let's say, safety factor. So I need 50. Okay. What I'm trying to do now, I'll try to take the gain in here, from here. I want to force the system to have the crossover frequency at this point. So I am, you know, they call it, you know, gain attenuation. That, you know, I'd like to take out at the phase margin, at the new phase margin, which is I can read from the system phase, and I want to drop the, you know, gain by 20 dB. Okay, so what we will do, look, moreover, okay, moreover, when I add my compensator, if I add the compensator, suppose I add the compensator in here, I try to take from this one, I'll take minus 20. But if I add the compensator here, what will happen to the phase also? Because of this negative, what will happen? What will happen to the phase? The phase will change. So
That's what we want.
what?
That's what we want, right? The
Yes,
phase.
the phase, okay, I need the phase of 50 in the system. The phase, my phase margin, I want it to be 50. If I add the compensator in here, I'm going to affect the phase as well. What they have done, okay, they try to position the compensator 1 decade before this point. Okay, they want to position 1 decade before this point. Because look, if you position 1 decade before, do you affect the gain? The gain is not going to be affected. But what will happen to the phase? The phase after 1 decade, it will be 0. So it will not affect you anymore. If I position my compensator, not here, 1 decade before. So what will happen at the end, okay, I will affect the phase in here. However, the phase margin, required phase margin, is not being affected by this, even though I am taking out some gain. And this is the way it will be done. I'll go over it again next lecture, because now we have to stop for the quiz. Okay, we will be